Hello, class. Let's continue our discussion on radical halogenation reactions. Recall from general chemistry, Gibbs free energy equals the change in enthalpy minus the temperature times the change in entropy. Remember that equation? Well, what we're going to do is use this equation to understand the difference between halogenations using fluorine, chlorine, bromine, and iodine. They all behave a little bit differently, and it has to do with Gibbs free energy. So when we take methane here and we treat it with our halogen, and we're going to add some light. We're going to do a radical reaction here. We are going to get, we can go CH3 right there like that, and then put our halogen like so. Okay. And then we would also get our HX. Okay. Like that. So when we look at Gibbs free energy, we have an entropy term right here, which is the amount of disorder. So what we have is 2 molecules on the reactant side and then 2 molecules on the product side. So what we can say is the entropy change right here is going to be negligible because it's going from 2 to 2. So what we can do is really just focus our attention on that. We can roughly approximate, kind of just approximate here, that if we can calculate the enthalpy, that's going to equal the Gibbs free energy. And recall, a reaction is going to be spontaneous or favorable if the delta G is negative. So in order to calculate enthalpy, we can start looking at bond association energies. And to help us better understand what's going on here, I'm going to expand this out, showing bonds like that, and then like that. So what we have to figure out here is in order to get this reaction to work, we are going to have to break bonds and form bonds. Now I'm just redrawing this so we can get a better idea of what's happening here. So do you see that we have to break this carbon-hydrogen bond, and we have to break this halogen-halogen bond. And then we are forming a carbon-halogen bond and a hydrogen-halogen bond. So what we have over here are bonds broken and bonds formed. Like that. So recall the equation that the change of enthalpy is going to equal the summation of all the bonds broken okay. Well, to be more precise here, it is the enthalpy, the sum of the enthalpy of the bonds broken, minus the summation of the enthalpy for all the bonds formed. Like that. So what we have to do is then go into our tables and take a look at the bond association energies for the halogens of interest. So the ones that I want to look at, let's take a look at fluorine. So I'm going to replace those with fluorine. And so I go to the bond association tables and I ask or look at the table. It says, how much energy does it take to break this carbon-hydrogen bond? And I look at the table and it's 435 kilojoules per mole. And a fluorine-fluorine bond is going to be 159 kilojoules per mole. forming a carbon-fluorine bond is going to be 456 actually, kilojoules per mole. And then F bond is 569 kilojoules per mole. So we just got to use this equation right here and sum it all up and then subtract it. So bonds broken right here, we would just go 435 plus 159. Add those together, and then we would have to minus the sum of the bonds formed. 456 plus 569. And that's going to equal the change in enthalpy. And when we type that into our calculator, we are going to get an answer of negative 431 kilojoules per mole. That's how much heat or enthalpy is released, typically in the form of heat. That's a lot of energy. And since we know enthalpy in our situation here equals Gibbs free energy, I know that this reaction is going to be spontaneous and favorable because we have a negative delta G. And so what we have is a exothermic process. Okay, so now you could do this same math if you're looking at chlorine, bromine, iodine. And when you do all that math for each one of those halogens, you're going to see something very interesting. So when we do this reaction for fluorine, that's our answer. It's exothermic. So when you do it, so this is for fluorine, okay? But when you do the reaction with chlorine, the answer is a little bit different. It's a negative 104 kilojoules per mole. And that is for our chlorine. Let's see, next one, we could do bromine. And bromine is a negative 33 kilojoules per mole. That is bromine. And then the last one is iodine, which is going to be a positive. Actually, it's going to be a positive 55 kilojoules per mole, and that's going to equal our iodine. I2, you can't see that right there. So I'll put that equal sign and say, hey, let's go over here. That would be our iodine. So what are we seeing here? Fluorine is exothermic because it's negative, so it's favorable. Chlorine, negative. Bromine, chlorine. But iodine is positive. So iodine is endothermic. And because it's so endothermic, the reaction isn't favorable. So when we want to do halogenation reactions under radical conditions, it's just fluorine, chlorine, and bromine that are exothermic. And so those are the only ones that could actually do anything. But look how drastically different it is of fluorine to chlorine. It's a huge difference in energy. And that's going to have some implications later on. And then when you compare bromine and chlorine, they're different as well. Not as drastically different as fluorine, but they're different enough that we can use this difference in energy to our advantage. And we'll talk about that later as well. Now, so this was all done when we were looking at methane. But if you did this same process with, let's say, ethane, you'll get similar results. The numbers are going to be slightly different because now we're dealing with ethane, but very similar idea here. So what I want to now do is take a look at fluorine once again. This is so exothermic that trying to do this reaction, it's dangerous. It's explosive. And because it's so explosive, it's just not practical to make this compound this way. because it's so exothermic. So we don't do halogenations with fluorine. We just don't do it. So can't cancel it out because it's so reactive. We can also cancel out doing halogenations with iodine because that is just too darn slow. So it's really just these two halogens right here that we are going to use in halogenations. So now I want to take a look at the differences between these two when we try a halogenation reaction with ethane. So now I want to take a look at ethane right here, reacting with the chlorine radical. So I'm skipping the initiation step and going straight to the first propagation step. And so what we're going to do here is when you do this reaction, we're going to have the first propagation step, which would then give us a radical right there. And then you would generate our HCl like so, just like that, right? And then our next step would be to take our radical right here and treat it with another chlorine radical right there to form our bond like that, right? But what I want to do is kind of do this stepwise and compare it to bromine and look at the energy differences here. So I'm thinking I'm going to redraw this so we can understand this a little bit better. Let's do that. So let's look at the first propagation step in this way. We'll do it more like this, shall we? And then we have our chlorine radical right there. And that's going to go and form this. Let's keep the bonds separate here. Like that. So what do we have here? We have to break this bond, and we have to form that bond. And when we do that process with chlorine, how much energy did that cost? Well, with chlorine, it's a negative 21 kilojoules per mole. And you can't see the kilojoules per mole there. I cut off the screen. But negative 21 kilojoules to do that process. But in comparison, when you do this reaction with, say, bromine, goodness, we're going to have the bromine radical already made. So we're doing the first step in the propagation. And then that would give us this. That would give us our radical plus our HBr. Now, both of these are the first step, the first propagation step. Okay, and that's the first. Now, how much energy, what's the enthalpy change for this process? So make sure we understand this is the change in enthalpy there. And that one is a positive 42 kilojoules per mole. So that is, this process right here is exothermic. That first step is endothermic. So which one's more favorable between the two? Well, it's going to be this one because it's exothermic, right? So what we can do is represent that first propagation step with an energy diagram. And let's think here. Do we want to do the energy diagram now or later? Let's do it later. Okay. So now let's take a look at the second propagation step. Okay. So this is going to be our second propagation step. So now what we have is we have our radical like this, our radical, and we are going to treat it with another chlorine molecule here. And so we're doing our halogenation step or halogenation abstraction, and that's going to give us our product like so. Chlorine plus. So what have we done here? We have to break this chlorine-chlorine bond. We form that chlorine-carbon bond, and that's going to be worth a negative 96 kilojoules per mole. So exothermic again by a lot. But when we compare using this one right here, so let's use the right color. Radical, and now we're treating that with bromine. So that's going to give us another radical. Now that process is going to be negative 92 kilojoules per mole. So both of those, in the second propagation step, both are exothermic and are favorable. Now remember that when we sum up all of these pieces here, remember when we look at the overall reactions, we have to look at the bonds broken minus the bonds formed. And when we do that for both of these reactions right here and sum it up, what we're going to find is that chlorination, so we can say chlorination, Cl2 here, the overall enthalpy change, or the Gibbs free energy, is going to be a negative 117 kilojoules per mole. So very exothermic, very favorable. Also, when you look at bromination, it's also going to be negative, but just slightly less, 50 kilojoules per mole. So both are exothermic, both are favorable. But now when we take all of this, all these numbers here and apply it into a graph, we're going to see something. I hope that you can see it and be like, oh, this makes more sense now after looking at the graph. So we're going to take all these numbers, put it into a graph form, and understand the reactivity of chlorine versus bromine. What are the differences? So let's take a look at chlorination first. So the first step, or the first propagation step in chlorination, the energy diagram would look something like this, right there. And from this point right here to this point, that is the first propagation step. Okay? So on your x-axis right here, what you're looking at, okay, this is when the reaction starts, and this is where propagation 1 ends, right here. All right, so that's from there to there, that's the first reaction. And what we observe here is the numbers that were given to us when we did those calculations. We noticed that from here, okay, to here, there's that energy difference right there. Okay. And what was that value between that? That was a negative 21 kilojoules per mole. Do you see how that's exothermic? The starting material is higher in energy than the product. It's lower in energy, so that's exothermic. And when you compare it to bromination, it looks a little bit different. Bromine is larger, more stable, than the chlorine. So what we have is it starts at a lower energy, but it has a higher energy of activation, like so. And recall the value for bromination, or in the first reaction. That's from here to there. That's the first reaction, or the first propagation. What did we say the value was? We said it was endothermic, right? Because look at that distance there. That's where we started. That's where we ended up. And we said that was, what was the value? That was a positive, we'll do it right here, a positive 42 kilojoules per mole. Okay, so do you see now that first step right there in the reaction, it's endothermic because that product right there is higher in energy. But really, that's technically not the product. That's called an intermediate because remember, you have to do the second propagation step. And that's what this part is. From here over, what does that graph look like now? It's going to keep going up a little bit and then come back down over here, right there. So this is technically an intermediate. And so when we take a look at the energy difference from this intermediate to the final product, if we extrapolate out there, what is the energy difference there? That was calculated to be a negative 96 kilojoules per mole. So you can see that from here to here, this is the second propagation step. And it is once again exothermic because we started here and we ended at a lower energy. Isn't that cool? Now, if we compare that to bromination, now what does the bromination curve look like? Well, it's going to come up a little bit and then come back down over there. So look at that. So we are now, if we propagate over here, like that. Oh, that's a horrible line. From the ending spot to where it started over there, you can now see that distance is going to be a negative 92. A negative 92 kilojoules per mole. So overall, what's the overall enthalpy change? Well, that would be the distance from here. So we'll propagate, extrapolate, I mean, over there to there. So this distance there is what? That was the negative 117 kilojoules per mole. But then when we look at bromination, extrapolate that out. So the distance between those 2 points, this point and this point, we see is going to be a negative 50 kilojoules per mole. You can't see the 50. Negative 50 kilojoules per mole. So what can we learn here? Which one is more favorable? Well, chlorination is more favorable because look, it has a larger delta G, more negative than 50. But also take a look at the energy of activation. So this distance right here, that is the energy of activation compared to this energy of activation right there. So chlorination, based off of kinetics here, is going to be a whole lot faster than bromination because the energy of activation for chlorination is so much smaller than the energy of activation for bromination. So this reaction right here, bromination, does occur. It just occurs more slowly because the first step is the rate determining step. And it takes a long time to get over this hill. This is also the rate determining step, but it's just a smaller hill to climb, so it goes a whole lot faster. So this speed, or the rate at which these reactions occur, both will occur because you can see overall it's exothermic. But the rate at which they occur, we find that bromination goes slower, and we are going to be able to use that to our advantage. And I'm going to show you and talk about that later. But just know that because of the differences here, we can utilize those differences for our benefit. Okay. I'm just double checking, make sure there's nothing else that I need to say about this. Okay. Now let's shift our focus to the selectivity of halogenation. So for example, let's take propane now. If we take propane and do a halogenation reaction, we can have two possible products. We could put the halogen on that carbon. So if we label them 1, 2, and 3. And we could have also attached to carbon 3 or carbon 1. Same difference, right? So those are the two possible products there. Which one do you think would be favored though? Well, if you analyze it like this, which is not the correct way, mind you, if you take propane, you see that on the carbon 2, you have 2 hydrogens. So once you form our radical, right, this radical could abstract this proton or that proton. But then when you look at these, the terminal methyl groups here, based off of statistics, you would be like, okay, carbon 1 and carbon 3 are the same, but there's 6 hydrogens total. So statistically speaking, what are the odds of this halogen radical here to abstract one of these 2 or one of these 6? Right? So you would think that this would be the major product because there's 6 hydrogens that this radical could abstract. In contrast, this product, there's only 2. Make sense? I hope. Statistically speaking, that makes sense. But statistics isn't analyzing and looking at the energies here. That's what we need to actually look at. Because if we take this and turn it into this and do a hydrogen abstraction and turn it into that radical versus doing the same reaction but this time forming a primary radical, which one is more stable? Which one's easier to form? We know the answer. We've already talked about this. The secondary radical is going to be way more stable and more likely than the primary radical. So when we do this reaction, this is going to be our major product, and this is going to be our minor product. And in some cases, none at all. And that depends on if we're using chlorine or bromine. But before we get to the differences between chlorine and bromine, let's look at it energetically, why this is the case here, or why this is the major product. I already explained that it is because we have a more stable secondary radical. But if we look at the potential energy on the y-axis and the reaction coordinate on the x-axis right there, the hydrogen abstraction step right here is going to look like this. We'll have energy will come up and then we'll come down like that. Okay, so there's an energy diagram right there. But look at what happens if we draw another line here. Let's draw it in green here. Okay. So what's the difference here between these two? Well, this one in the pink, that's going to be our secondary radical. It's easier to form because the energy of activation right there is smaller in comparison to the energy of activation for the primary radical. Also, why is the secondary radical more stable and more likely to form? Because it's lower in energy when it gets to this side. Now, why is this more stable? Remember hyperconjugation. So go back to that principle there. Hyperconjugation helps to stabilize this radical. But from an energetic perspective, that is why this product is going to be favored, because it has a lower energy of activation and it's more stable. Now let's take a look at when you replace this right here. Let's replace the halogen now with chlorine. So what is going to be our major product here? Well, this is going to be our major product. This is going to be our minor product. But look at the ratios here. This is interesting. This is approximately 60%, and this is 40%. All right. So the difference in energy between these two is not drastically so different that it's going to make this like 100%. But look at what happens when we change it to bromination. Now this is very interesting, and I think it's very cool to see this. If we take propane and treat it with bromine now, we will get this product. And so 100%, none. It predominates on this one. So isn't that crazy? A crazy difference there. Chlorine is 60% major, and this is 100% major with bromine. Why? What is going on here? Well, energetics can help us understand what's going on here. But you have to remember, go back in your notes to remember the energy diagrams that I drew for halogenations with chlorine and then bromine. Remember how they look different, and we calculated those numbers. So we need to remember that as we are discussing why its bromination is more selective than chlorination. So why is there a difference between the selectivity of halogenations when using chlorine versus bromine? Well, it comes down to the Hamett's postulates. Remember, that is looking at what does the transition state look like? And the transition state is that part right there, our transition state. Remember that the Hammett postulate is telling us that the transition state is going to look like, well, it has two options here. If we just separate it, like separate and distinct, the transition state could look like the starting material, or the transition state could look like the intermediate. It's the same thing here. Does this transition state look more like the starting material or the intermediate? Now, this energy diagram is the first propagation step. So if we looked at it, so we're looking at propane. So what we're looking at is this first step. When we take our radical halogen right there and we do the hydrogen abstraction to form our radical. That's what we're looking at right here, that first propagation step. Okay. So what we're trying to figure out here is this transition state is closer to which reactant or intermediate. So you can see from this point on the y-axis to this point, it's that distance right there, right? But if you look at it from this point to this point, you can see there's a bigger energy difference, right? So what Hammett postulate is saying is that the transition state here is going to look more like the starting material than it does for the intermediate. in contrast, when you're looking at this energy diagram, which is being represented for bromination, and this one on the left was for chlorination, if we ask ourselves, based off of Hammett postulates, the transition state here, what does it look like? Does it look more like the intermediate or the starting material? For bromination, the transition state is going to look more like the intermediate. So let's recap so far what we've done here. The transition state for chlorination looks more like the starting material. The transition state for bromination looks more like the intermediate. You see how they're looking like different parts on the energy diagram? That is why we have the selectivity that we do. Because when we look at the transition state for chlorination, right here, we could represent it kind of like this. I'm going to draw the propyl like that. And at the transition state, that hydrogen is starting to break, right? And then starting to form a bond with the chlorine atom. So I'm going to draw it much longer like that. So what's going to happen here is that we are going to have a partial radical right there and a partial radical. Okay? So what's our goal in this first step? It is to abstract that proton. Now contrast that with when I draw it with bromination here. Like so. That's a radical and a partial radical over here. That's what I'm drawing there. That's what those delta symbols are. Partial negatives, partial positives, but now we can have partial radicals. Now you take a look there. Do you see the difference? In the transition state for bromination, this carbon-hydrogen bond is mostly broken. So we mostly have radical character for our propyl group. But in contrast with chlorination, the carbon-hydrogen bond is basically more formed than broken. And so we have less radical character. And so it's this difference here. Because this has more radical character, we've learned a few minutes ago that we want to have a secondary radical because it's more stable and lower in energy. And so because this is more radical-like, it is going to predominantly be the secondary radical in the transition state. But because this is not so radical, it basically can go between. It's not very selective. Because it's not so much radical, it could be secondary or primary, and it's not that big of a deal because the transition state looks more like our starting material, which isn't radical. It's radical over here at the intermediate. And so that's Hammett postulate in practice. And due to this, we know by observation and based off of this theory and explanation that bromination is going to be way more selective than chlorination. That is a very key piece of information to remember. And more importantly, understanding why. And it's shown right here. So let's take a look at another observation here. Now let's take a look at this butyl compound here. When we do chlorination, what's going to be interesting is we're going to get 65% of the primary and only 35% of the tertiary halogen, or quaternary halogen. Let's do tertiary, sorry. But when we do same starting material, but just do bromination here, what do we have? We have 100% and 0%. Now it's very more selective here. Now, let's take our attention here on draw the energy diagram for this one and see why we have so much selectivity. So we're going to do the first part, the first propagation, where we abstract the hydrogen. And what we have here is we have an option to abstract one hydrogen off the primary carbon or this one at the tertiary carbon, right? So what does that look like? Well, we're going to have an energy difference like that, like so. And then we can have another one that looks like starting at the same spot right here. Right. Let's make it a little bit more drastic, shall we? Just so we can make a point here. All right. So what's happening here, this is going to give us our tertiary radical, and this is going to give us our primary radical. All right. So you can see that they're drastically different. When we compare over here, let's see here, we could do chlorination was starting up here and like this, like so, right? So that's going to be our primary radical. But look at what the tertiary radical looks like. Do you see how they're not drastically different in comparison to bromination? So let's, yeah, so we understand that this is chlorination and this is bromination, right? Yeah. That's important to remember. That's 2. Okay. So another reason why bromination is more selective than chlorination is because when you're comparing your primary versus tertiary radicals, there is a huge difference when you do bromination versus a tiny difference in chlorination. And so why then would you expect this one to be the major product, even though it gives you the primary radical, which is the least stable? It doesn't make sense. But then again, it does, because there's basically really no huge difference in this transition state between the primary and the secondary radical. And so now it's basically statistics at play. So we could be like, hey, there's only one tertiary hydrogen, and then there's going to be 9 primary hydrogens. So there's 3 right here, 3 right there, and 3 right there. So there's 9. Because this transition state is so close in energy, there's going to be no selection for one or the other. And then it's just a numbers game. There's 9 primary hydrogens and only 1 tertiary hydrogen. So that's why we're going to get the majority of the product with the primary alkyl halide. But if this energy difference at the transition state was much larger, like this, then you can see that we select for only 1. Kind of crazy, isn't it? But that's the reason why we see these differences in selectivity. So now we have to look at stereochemistry. What if you have a molecule like this, and let's say you do chlorination right here? You could have adding the chlorine there, or you could have added the chlorine at the primary position, right? So what if you make an alkyl halide that is now a stereocenter? So do you have it like this, or is it like this? Well, the answer is quite simple. Because we have to just remember what that first propagation step looks like. That first propagation step is going to be a hydrogen abstraction. So you're going to generate your secondary radical like that. Remember what we said about the the geometry of this radical. We said that we can make the assumption that it's trigonal planar, that it's completely flat. So if it's completely flat, then that means when you do the next step right here, when you treat it with another radical right here, right? There's a radical. And we can come here like this and form that carbon-chlorine bond. Well, since this radical is flat, that means this radical can approach the top face or the bottom face with the same probability. So when you go and make a stereocenter, you are generally going to get a racemic mixture. You're going to get 1 to 1 because of the geometry of that radical. Now, let's see here. What if you have a molecule that is already a stereocenter and you do radical halogenation? What happens to it? So what if we have this molecule and we wanted to do bromination? And we see that we can generate a tertiary radical. And we are going to replace this hydrogen right there with the bromine. So do you see, before we do the reaction, that is a stereocenter. And then after the reaction, it is still a stereocenter. So what do you get? Do you get one enantiomer or do you get both of them? Well, it all goes back to the geometry once again, because once you abstract that proton off, what do you generate? You generate a radical. And that's going to be our methyl group still. So that methyl right there is that methyl. That's flat. And so the bromine radical can approach from the top face or the bottom face with equal probability. So your product is going to be racemic once again. But now we can have a situation where you have a molecule that's already has a stereocenter. All right. So let's do something like this. CH3. And let's do bromination. All right. What's going to happen here? Well, there's no hydrogens on that carbon, but there are some hydrogens there. So we'll abstract one hydrogen there. And I'm going to actually add another carbon because I need that carbon there, okay? So what would the product be? So that stereocenter was never touched right there. This stereocenter was never touched. But what has now happened? We have now converted that other carbon right there into a stereocenter. So what's going to happen here now? Well, this one's going to be interesting because now what we're forming are diastereomers. So if we compare the wedged bromine versus the dashed bromine, and we still have that OCH3 and our methyl, our double bond there. We can still finish our methyl there. So the relationship between these two molecules now are diastereotopic. So yes, when we do the abstraction and abstract that proton, we are going to have a radical there. So that carbon right there is going to be planar. But you have another stereocenter that has different groups. So what you're going to have is no longer a racemic mixture, because when you make diastereomers, the approach of the radical, bromine radical, is going to select maybe the top face or the bottom face. It's going to have to make a decision. And so let's make this a little more drastic here so you can see the difference here. Okay. So what if I change that to a hydrogen? No, not a hydrogen. Let's keep it a methyl, but change this guy right here to a terbutyl. Okay. Now, which group is going to be the most bulky? Clearly the terbutyl oxide right here, right? Much more steric bulk. So when we have this planar carbon right there, we still have this terbutyl that's coming out at us. And then we have a methyl group that's behind the molecule. So let's just envision my hand again. And my hand is representing this carbon radical. And then over here on my wrist, I have this big terbutyl group over here. And then underneath my wrist, I have the smaller methyl group. So if my hand is the radical, what side of my hand do you think this bromine wants to approach? If I have a big terbutyl on the top of my hand, the bromine is going to have a harder time approaching from the top face. So it's going to much rather approach from underneath, because underneath is just a smaller methyl group. And so this stereocenter right here kind of directs or influences which face of this radical the bromine is going to attack. And so when you do this reaction, can you predict which one's going to be the most prominent? Not in this example right here, because these groups right here, their bulkiness is very, very similar. But when you have, say, something drastically different, then there's a good chance that we could predict it. And so we would not want to attach the bromine on the same face as the terbutoxide right here. So this one right here, the bromine is approaching on the same face as the terbutyl group. So if I had to make a choice, which one would I think would be the major product? I'd say this one, because the bromine is attacking the opposite face of that terbutyl. So I hope that makes sense. And if you have any questions, please reach out. I'll be more than happy to help.